Okay. Now let us see how to control a diffusion flame. See, as I told you, diffusion flame has a wide operating range when compared to a premixed flame. Okay, this because of the basically when you increase the flow rate, the flame length increases and it completely burns wherever you find it finds the enough stoichiometric air. So that will define the boundary of this flame also. So in that case, now it is very simple nature, but only thing is you will end up in some emissions. So how to avoid those emissions, how to have better control of the combustion efficiency, etc., that we will see. So if you take the extent of a flame, so for example, if you have a same jet flame, okay, so the extent, when I say extent, I say the flame width or the flame height. So flame height is very important as under the flame width, or say flame radius or flame diameter. Okay, so if you take this flame radius, so the flame radius or the flame width or flame height, etc., are called extents, and this the extent is one of the characteristic, burning characteristic. Flame length is one of the important burning characteristic. Okay, then formation of CO, soot, nitric acid, the burning characteristics. Okay, so this for example, when you don't, when the diffusion control fuel doesn't get enough oxidizer, end up in formation of CO. Then based upon the fuel type, okay, soot formation can be there. Based on the flow rate and availability of oxygen, etc., soot formation will be there. Similarly, nitric oxide. Nitric oxides are not much in the diffusion flames when compared to the premixed flame. Premixed flame, nitric oxide emissions will be slightly higher. Okay. Now, so to control these, the extents, okay, the main characteristic of the diffusion flame is the flame length. Then the burning characteristics are formation of CO, soot, nitric oxide, etc. We can go for several configurations. When I say configuration, the way with which the fuel and oxygen are supplied, okay, that is configuration. Similarly, I can control the flow rate of both fuel and oxidizer. Okay, so if you take a jet diffusion flame, okay, only fuel is supplied in a forced convection, correct. So due to the momentum and the viscous effects, you can see that the entrainment of air takes place, and in this case, no, there is no control. When you want to just control the flame length, only the volumetric flow rate of the fuel can be changed. But volumetric flow rate has to be supplied in a given ratio. See, for example, if I want to operate the burner in a fixed ratio of power, for example, maximum power to minimum power, then the flow rate also will correspond to that maximum and minimum, so minimum values. So how will you control the burning characters? If I say when I operate the burner in a minimum flow rate, there may not be much emissions. Even soot which is formed, that may be oxidized within the flame itself. However, when I go to the maximum limit of the burner operation, then I may get more CO, which is not as per the standards. Then I can also get more soot and so on. So how to control this? That is the main thing. So in this case, basically the jet diffusion flame, the extent and the burning characteristics are dependent only on the momentum. So that means that when I don't have any control, other control, then we will be in trouble. So what to do for that? That is what adding some amount of diluents to the fuel stream, adding some primary air. So these are the techniques which we will use. So why we use it, we will come to that. So basically, based upon the fuel type, when I again stress the factor fuel type, that means every fuel is not so bad. For example, methane is a very nicely burning fuel, okay, because it has only one carbon atom and 4 hydrogen atoms. So it actually, the H/C ratio is 4 and it burns nicely. However, when you go for say higher order hydrocarbons, say heptane, etc., you will see that there will be when the fuel has to pyrolyze to smaller hydrocarbons, and when it does, then we will also end up in unsaturated hydrocarbons like C2H2, C2H4, etc. So those are the unsaturated hydrocarbons, etc., can form soot. Even cyclic hydrocarbons, aromatics can also be generated. So when you go for heavier and heavier hydrocarbon fuels, so in such case, what happens is the soot formation becomes unavoidable. You cannot avoid soot formation. Okay, but how to control the soot? Say if the soot, let it form. There's no harm in that. Soot which is formed, If it is oxidized within the flame, no issue. So, for example, there is a flame, okay. So, soot is formed somewhere, some location soot is formed, but soot is also oxidized in this region. So, there is no soot in this position. So, there is no, these are the hot products which are leaving, correct, hot products are leaving here, flame tip, but there is no carbonaceous particle. Soot is nothing but a carbonaceous particle, small particles that are grown to some size, and they are not leaving here. So, if the soot formed, and this is oxidation, okay, when the soot is formed, is oxidized within the flame, there is no issue, but that will not occur for all the flow rate. So, it is actually based upon the fuel flow rate and oxygen availability. Soot is oxidized within the flame, it is good if it is done, or if it is not oxidized within the flame, the soot will leave along with other products, CO2, H2O, some amount of CO, unburned hydrocarbons and so on. If that is the case, then that is treated as an emission. So, smoke, you will see smoke coming out, okay. So, that is what is illustrated here. So, let us take this, there are 4 cases given here. At low flow rate, you can see that there is a, this is the typical diffusion, jet diffusion flame. You can see there is a blue region here, where the fresh oxygen comes in and lot good premixing occurs, and as the flame height increases here, you can see that bright emission, you can see the bright emission, that is due to the soot formation, and soot emits this bright emission here, and but within the flame the soot is oxidized also. So, within some region here soot is also oxidized, so that nothing is, no carbonaceous particles leaves the flame. Similar here also, same regime, a bright regime, and the soot oxidizes here, no soot leaves the flame tip. So, flame tip is intact. So, I say the flame tip, it is intact like this, but go to this figure. So, I am just increasing. So, this is the increasing QF. So, QF increases, okay. When the QF increases, I see the replication, that when QF increases, the flame height increases. Also, other characteristics changes. So, basically, if you see these 2 flames, there is no difference in the characteristics, a bluish base, bright middle portion, and the tip is nicely closed and so on. Now, go to this higher flow rate QF3, you see that this is there, again some bright emissions are there, but soot is not able to fully oxidize at this flow rate. What happens here? You can see the tip is open, and now you can see some smoke coming out. So, this is the smoke which leaves. So, here you can see the same thing, a tip opens and give good amount of smoke. Good amount of smoke leaves the flame. So, please understand that the same fuel is used here, okay, which is heavier hydrocarbon, this is LPG flames. So, you can see that in the LPG flames at low flow rates, soot which is formed radiates that it has formed. So, bright color and the luminous radiation is due to soot. So, that is there. Then soot is not able to oxidize. So, it is able to oxidize also, sorry, in this first 2 cases it is able to oxidize also, the flame tip is closed and fluid is fully oxidized. And when go to a critical flow rate, you will see the flame tip opens up and the carbon particles leave. So, this is we call smoke. Okay. So, this is visible smoke, here also you can see visible smoke. So, flow rate at which visible smoke is exhibited from the flame tip is called smoke point. So, this flow rate where the tip opens and visible smoke is seen, that is called smoke point of this particular fuel. So, LPG at a given flow rate, you will see that smoke is formed. Till that, now no smoke is seen, because soot forms oxidizes within the flame itself. So, no soot is leaving the flame. So, these are well within the smoke point flow rates. So, flow rate at which visible smoke is exhibited, that is called smoke point, and that is a fuel, again depends on the type of fuel. So, type of fuel will do this. So, In these cases, when the flow rate is less than the smoke point, the soot is oxidized within the flame, or else the soot is, if the soot is not oxidized within the flame, then the tip opens up, the smoke comes out. So this is the illustration for that. Okay. So so please understand that. But I want to operate my see, this may be the lowest flow rate of my burner. This may be the highest flow rate of my burner. But there is no problem when I operate in the lowest flow rate or low flow rates. But when I go to higher flow rates, so power requirement is higher. So I want to increase the flow rate and operate my burner. I see that I don't satisfy the emission norms, where I now throw out the smoke into the atmosphere, which is not correct. So some control has to be done in this to avoid the smoke which is released out, or the soot which is unoxidized leaving the flame tip. So this has to be taken care. Okay. So we need control for a diffusion flame in such scenarios. So how to do this? Okay, now I will discuss more about which type of fuel will form more smoke and so on. So that for that now smoke point experiments, standard ASTM experiments are there. So ASTM standard experiments are done. So basically it started with liquid fuels. For liquid fuels, when they burn pool, if you have a liquid fuel pool, it will burn with a diffusion flame, and when based upon the diameter of the liquid fuel pool, you will see the smoke coming out. Okay. So the smoke point was judged like that. Further, it was actually extended to the gaseous fuels also. Smoke point basically is the, as I told you, is the lowest flow rate at which you will see visible smoke coming out of the flame tip. Okay. Now let us take saturated hydrocarbons, say propane, heptane. Okay, N-heptane. This is okay. Now saturated hydrocarbons, you need higher flow rates to form the smoke. So 7.87 milligram per second, 5.13 milligram per second. So normally we have in small burners kg per hour. So that is the flow rate. So either milligram per second. So that is given. So this is somewhat higher. Why I say this higher? Because relatively. So on the other hand, if I take unsaturated species, hydrocarbons like propylene, acetylene, etc., you can see that the lower flow rate itself will produce smoke points like 1.12 milligram per second for propylene and 0.51 for acetylene. So these are the fuels which will form more and more soot basically, and soot is not able to oxidize even for a very low flow rate like this. So it's if you compare to heptane, it is only at 10% of the flow rate, but you can see smoke point is reached. I am not able to control the soot oxidation. Soot is not oxidized within the flame and the smoke comes out. So that is the problem. Go for aromatics, cyclic hydrocarbons like toluene. You see that still half of the acetylene it has the smoke point flow rate. So based upon the fuel type, if you have unsaturated hydrocarbons, cyclic with 2 bonds, etc., then you will see that there will be tremendous potential to form smoke. That is, the soot which is produced will be produced at a faster rate, higher rate, and it cannot be oxidized within the flame even for a very low flow rates like this, resulting in smoke leaving the flame tip. So this, for these fuels, understand the fuel. This is called fuel characterization. Understand the fuel, and based upon the fuel characteristic, we need to control the diffusion flame, or else no, we cannot have we cannot operate in wide range. The flame may be stable, but the emissions may be not under control. Okay, so that is the main thing which we will try to do. So how to do this? So if you take jet diffusion flame, these are all jet diffusion flame characteristics. Basically, I don't have any force flow for the oxidizer. So only fuel comes out and a flame forms, and based upon this the tip opens or not, whether the flame is closed or not, basically depends on the smoke points and so on. But so if how I increase this, how will I, so why is this is happening? Because the rate at which oxygen is trying to enter the flame zone is not enough. The momentum, so the momentum of the jet is not able to entrain enough oxygen in order to oxidize the soot and so on. So how to increase the oxygen availability for the fuel? That is done So in order to have increased control, okay, oxidizer is also supplied from a separate flow port via forced convection. Instead of allowing the oxygen only to naturally entrain into the flame, we will try to supply oxygen also in a forced convection. Okay, then convective heat the mass transfers will be higher than a diffusive mass transfer. So that will enable us faster mixing, correct. So if we do so, then we can see that we can try to control soot and CO emission. That means we will have more control over the flow of the flame at a higher flow rates also. So that is the category we are going to address here. So how to do this? So based upon the direction of the oxidizer flow, see when I plan now to supply oxygen forcefully, like in a forced convection through another port. See, obviously we cannot supply oxygen in the same port because it will become a premix flame. Partially we can add some oxygen or oxidizer to the fuel port, that is called primary air only. But please understand that fuel plus primary air normally is kept out of the flammability limits. For example, if you have only the primary air and the fuel coming out, you try to ignite it, it will not ignite unless additional air is provided to that. Okay, so it will not have enough oxygen to burn. So that will be the primary aeration which we do. Okay, because now if you have a mixture of fuel and primary air which is flammable, then flashback instability also will come into play, because the flame will ignite and can flash back when the flow rate of the fuel and primary air is low. So in order to avoid that in industrial furnaces or domestic cookwares especially, we will not allow the mixture to be flammable which is coming out of the fuel port, but additional ports will be engaged to supply oxidizer. So separate ports will be engaged for oxidizer supply, and that will be done through forced convection. Okay. Okay. Now, if you based upon the direction of the oxygen flow, so we will categorize the configurations of the diffusion flame. Okay. So now how will you categorize? First is co-flow. Okay. Now fuel is supplied here. Oxygen is also supplied in the same direction as that of fuel. So that means I will have another port which is annular to this, okay, and I will supply oxygen here, oxidizer here basically, or air or oxidizer, whatever. So now you see fuel comes out of this flow, oxygen is forcibly coming out of the annular region surrounding the core fuel port. Now this is called co-flow. So the flow of oxidizer, direction of the oxidizer and the direction of the fuel are the same, correct. So that is the co-flow, co-flows, oxidizer co-flows along with the fuel. This is one configuration we have. Second is counter flow. So I can have a fuel coming out like this. Oxidizer will come out in the opposing direction, opposite to this. So counter flow, opposed flow also we can say, counter flow or opposed flow. Oxidizer flow opposes the fuel flow direction, it is exactly opposite to the fuel flow direction. Then another configuration is I supply fuel in this direction and oxidizer in this direction, okay, oxidizer in this direction. So they will be orthogonal to each other. So oxidizer flow perpendicular to the fuel stream, that will be the cross flow configuration. We can also do anything in between this. Okay, these are the configurations which we can use to build a burner, to have control over the dimensions of the burner, etc. So we can also have other configurations. Okay, for example, some angle oxidizer can come in instead of 90 degrees like this, cross flow and so on. So several configurations are available. These are the important configurations which people have used. Co-flow is one of the very well used configuration. Okay, so what are the characteristics of these configurations we will see. Okay, so co-flow configuration, as I told you, has been done from several years. Several researchers have been using this co-flow configuration, started by Burke and Schumann. This is very important research paper which actually established theoretical solution for a configuration like this. So what is this configuration is, there is a confinement. Okay, there is a confinement like this, and there is a flow of fuel in a central tube. Okay, fuel is supplied, and oxidizer air is supplied in an annular region. And please understand that so this is the co-flow burner Burken Schumann used for this, and theoretically and experimentally they analyzed the flames. So they saw two types of flames basically. One is called over ventilated flame, which is like this. Another one is like this, which stresses towards the wall, that is called under ventilated flame. So that means that I can have control of the flame by adjusting the fuel and oxidation flow rates. Okay, now please understand that entrainment of atmospheric air is completely suppressed owing to the presence of confining wall in this. Correct? So the fuel should find the oxidizer only from the forced convective oxidizer flow, which is co-flowing along with it. Okay, so now how the over-ventilated flame is formed? At a given fuel flow rate, if the oxygen flow is high enough, so sufficient oxygen is supplied, then what we get is a diffusion type of jet diffusion flame type of configuration. Sorry. Okay, a flame which is like this is formed. So this is the flame which is formed. That means enough oxygen is coming there and it will entrain. So oxidizer is actually entraining into the fuel jet, and wherever they mix at stoichiometric proportions, a flame is formed, and it is similar to the shape, similar to that of a jet diffusion flame. That is called over ventilated flame. On the other hand, if I do not supply enough oxidizer, the oxygen flow rate is less, reduce it. Then what happens? The fuel stream will try to expand towards the oxidizer and mix with this, and a stoichiometric contour forms here location. Stoichiometric mixing happens in these locations where the flame is formed. So such a flame which stresses towards the wall is called under ventilated flame. So this flame stretches towards the oxidizer side. It may not touch the wall, it may go towards the oxidizer side. Okay. So this is very important. So by controlling the transport rate of the fuel and oxidizer, I can get different flame shapes. So that is the control we have here. So we are supplying oxidizer in a convective force convective manner, plus we can control the shape of the flame etc. by just controlling the flow of fuel and oxidizer. So this is the numerical simulation of such a flame. Here a core port, that is the fuel port, core is fuel port of 4 mm diameter, inner diameter, some wall thickness may be there 1 mm, and you can see the co-flow pipe diameter is 30 mm. So it will have some annular space. Okay. So within the annular space air is supplied, and in the flow rate of methane in the core or the fuel pipe is has a velocity of 0.35 meter per second. And now when you have a velocity of the oxidizer, right, very slow flow rate of oxidizer, and if you see the velocity is about 0.2025 meter per second, 1 order of magnitude less than that of the fuel, you can see the flame is formed as a stretching towards the oxidizer side under ventilated flame. And please understand that the stoichiometric line is still open. The air is not enough for the entire fuel to burn. Some combustion takes place in this zone. This is the temperature contour in Kelvin basically. You can see that the dark region is about higher temperature where the flame zone is formed, and after that only after leaving the tube it may find enough oxidizer, but we may require to reignite the flame there. So based upon the flow rate of oxidizer, you can see that the flame actually stretches towards the oxidizer side, and this is called under ventilated flame. So the mass flow rate of methane is 2.8 into 10 minus 6 kg per second, and the flow rate of co-flow air is 4.5 into 10 power minus 6. Even though the air flow rate is higher, it is not even stoichiometric value. But if you increase the velocity equivalent to that of the fuel in the annular port, then you can see that the oxidation flow rate has now increased to 63.6 into 10 power minus 6, which is say for example, if this is 2.8 into 10 minus 6, this is 63.6 into 10 minus 6. So we have enough amount of oxidizer supplied. So we need 17 times, no, which is more than that. So if you do this, then you can see that you will get a flame which is exactly like a jet diffusion flame, but the control is if you can increase the oxygen flow rate so that more oxygen can enter. So basically what we have seen is if you increase the oxygen flow rate in a co-flow manner, co-flow flame, then the soot which is formed actually reduces after a particular flow rate. Okay, it will not happen initially if you just supply stoichiometric flow rate here. See, for example, if fuel flow rate is m dot f and the oxygen flow rate required for this will be equal to minimum is stoichiometric air fuel ratio into m dot f. So now if the oxygen flow rate is say 100%, then you get same amount of soot what you get in the flame, jet diffusion flame. On the other hand, if you increase the mass flow rate of oxidizer say to 200% of stoichiometric air and so on, you will get a reduction in the soot formation. So that means we have more control over the flames, the flame emitting characteristics basically. The flame height may not change much. Okay, the flame width may slightly reduce, flame height may not change much. However, the soot formation is actually reduced when you go for say this flow rate of air will be say 200%. So when I say this co-flow air is 200%, sorry, 200% stoichiometric air, etc. So then you get a reduction, okay, in the soot formation. So this is the characteristics of co-flow diffusion flame, and we will see the structure of the flame. Structure of co-flow diffusion flame is given here. Again numerical results, you can see that if you take these radial profiles are used here, and this radial profile is extracted within the potential core region of the jet, core jet. Okay, so you can see the for example, if this is the flow, okay, this is the potential core region for the jet. This is okay, this is fuel and these are oxidizer flow rates, and now in this region somewhere here the radial profiles are extracted, and you can see the mass fraction of the methane is 1 here, and it actually reduces and consumed at the flame zone. So this is the flame zone. So some finite thickness we have to give for the flame zone, and you can see this is the position. So about 7 to 8. So if it's the same region, you can see the heat release happening, the same region where the heat release peaks and the maximum temperature occurs, correct. So when the fuel and oxidizers are consumed in some finite thickness, then you can see that the maximum temperature and maximum heat release occurs at that particular position. Products are formed. So please understand that here the product mass fractions are very low. So we have multiplied this with some amount, say some factors, so to show the trends properly. So you can see that the water vapor, CO2, etc. are formed. Here some CO is also formed in this co-flow flame. Basically, if you can increase the co-flow velocity, you can also reduce the CO formation. So that is the way we can have control. So soot formation, CO formation can be reduced if you try to increase the co-flow air. So that just by making the air entry to the flame in a convective manner, which is faster than the diffusion, we can achieve control.